Right. Good day. Yeah, as I promised, today I'm looking at the Lenz law. This is part B. I'm going to call this part B. Right. For you to be able to follow this one, you need to watch my first video, which I called the Lenz law applied. Right. This one I've called it Lenz law applied part B. Right? So you need to watch the first video in which I was saying that when you move a magnet towards the solenoid, right, there is an increase if it is moving towards the solenoid. Yeah, there is an increase in magnetic flux around the solenoid. And if there is an increase, according to Lenz's law, the current will flow in the solenoid in such a direction so as to create a magnetic field which opposes the change. So what will happen is that the field inside the solenoid will be opposite in direction to the external field. The external field is the field from the magnet. So if you follow that first video, and if you're able to understand it, you'll be able to understand what we are going to be talking about here, because now you're not going to see the actual magnet. So let me start with this one right here. If you look at this, these crosses indicate the magnetic field into the page, right? And in the second case, these dots indicate magnetic field out of the page, right? So this, I couldn't make it a nice rectangular, but it doesn't really matter. It can be a circle. Yeah, a coil can be just a circle. If this coil, which is in this shape, is moving downwards, right? It's moving away from the magnetic field here, which is into the page, right? We are now going to say the field, the magnetic field inside the first solenoid, because there's a decrease, there's a change in magnetic flux. And that change in magnetic flux is a decrease, which means the magnetic field inside the coil will be the same, in the same direction as the external magnetic field. So in which case, if I take this part of the solenoid, because the change in magnetic field around the coil is a decrease because it's moving away. The magnetic field inside the coil is in the same direction as the external magnetic field. So it will be an X, it will be also into the page inside the magnetic field. You only take one section of this. Therefore, outside will be the magnetic field out of the page, right? Please, if you are a physical science teacher, if you are a student, right, don't mind my accent. You have to like my accent, right? You need to listen to this so that you are able to teach your students, so that you are able to, if you are a student, so that you are able to understand, and so that you can pass your metric. Okay. So this is, now you treat this as this part, any section of the coil. I take this section. If you use now your right hand rule for straight current carrying wire, right? So all your fingers, see this axis, should go in there and come out where there's dots. If you do that, you see that your thumb will point downwards. I'm sure you know how to use the right hand rule for current carrying conduct. So the current will be induced in such a way that it will flow down, right? Because the rest of fingers will enter here and come out here, right? You can try it for any other section, it will be the same pattern. So once it's going down like that, it means here it's going like this. And there also it will go like this. The current will flow in this direction. So this, you would say this is clockwise, right? If clockwise as you face the coil from this end, from the front, this is clockwise. I don't need to write the word clockwise. So that's how you do it. Please, 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 please pay attention. Pay attention. This is all you need to do. This is very easy, Max, right? The second option is, as you are moving, the external field is coming out of the page. As you move the coil towards the magnetic field, it is going to be an increase. There's going to be a change in magnetic flux around the coil. And you ask yourself, is this change an increase or a decrease? Yes, obviously, the the, the change, since the coil is moving towards the magnetic field, the change is definitely an increase. So if it is an increase, the field, let me take this side again, the field inside the magnetic field will be opposite. Yes, now it will be opposite because it's an increase. It will be opposite, like that, which is exactly like this one. And therefore, right. I'm doing only a few examples, and then you should be able to do. Now do the right hand grip rule for straight current coiling wire. You will see that the current will flow in a clockwise. Again, I just chose clockwise here. It will flow in a clockwise direction. That's how you need to do it. Very easy. Okay, let's look at this one. Here, the question can say, yeah, this is the coil, and there's a current carrying wire here. What happens at the moment you switch on? Remember, if you have got alternating current, for example, with your transformer, the coil, the primary coil is alternating current. Yeah? If you have alternating current, it means the secondary coil close by experiences a change in magnetic flux all the time, right? We don't use direct current because direct current can only create a change when you switch on or when you switch off. All right. So this question says, if you are just switching on here, then you ask yourself, during switching on, as the moment you switch on, there's an increase in magnetic flux. Okay, let's put the magnetic field around the current here. It is going to be, if you use your right hand rule again, so it means your fingers will, for the thumb to point downwards, your fingers will go in here. The rest of your fingers will go in here. If you use your right hand rule, and then it will come out here, right? So when you are switching on, right, and the external magnetic field for this coil, it is this one, which is close by, not this one. So when you switch on, definitely there's an increase in magnetic field. The change that it experiences is an increase, right? When you switch off, if they ask that question, I'm not going to do that one for you. That will be a decrease in magnetic field, magnetic flux around the coil. So let's deal with the increase. If this is an increase, the field inside the coil, let me use this side, the field inside the coil will be opposite because there's an increase. When you switch on, let me write on here, just in case you forget what we are talking about. Switching on, eh? So it will be opposite because there's an increase. So outside will be the same. Okay, it will be opposite inside, so outside will be the opposite. Now, if you use your right hand rule for this straight section of the coil, you see that the current, your fingertips will come out here, so the current will flow downwards here, down here, and also over here it will flow like that continuously. So it is anti-clockwise. Right, clear. Please, you should take your book and practice the rest of the questions. Right, let's try this one. This one is also very straightforward. There's two coils, one is inside, one is outside. But over here, the coil with current is inside, the other one's outside. Okay, so in this case, you want to know the direction of the current that is induced in the inner coil. In this case, you want to know the direction of the current that is induced on the outer coil. So, okay. So let's draw the pattern first. If the current is, your fingers are going in here, yes, just use your right hand rule. It's very simple. Very simple, very simple, very simple. And then therefore it's coming out here. Your fingertips are coming out here. If you grip it with your right hand rule for straight current for this straight section. So this is the field out. This one is closest to the coil that were of interest. So this is our external field. It is going into the page. Ignore that one, it's too far. So it's going into the page. So therefore, if the current is increasing, the magnetic field is also increasing. The bigger the current, the bigger the magnetic field around the conductor. So which means an increase, it means the field inside the coil, let me use this section of the coil, the field inside there will be opposite, which is an increase. It will be opposite the external field. Opposite this external field, which is close by, not that one. That is where learners make mistakes there, and they can't get it, they get the opposite answer. Right, and then here, if that is opposite, then outside it will be just the opposite of this one. So it will be X there. Then you apply your right hand rule again. Right hand rule again. In there, out there. So the inner coil, according to Lenz law, current will be induced, and it will flow in the anti-clockwise direction. So Lenz law is about the direction of induced current, right? So if you are stating Lenz law and you miss the word direction, you miss the word current, you miss the word opposed, you know you are probably looking at something else. Okay, I'm sure I don't have to look at this one. If there's a decrease, no, I think it will be too much if I give you everything away. Can you please figure it out? Start with this one. Now the current is decreasing, so the magnetic field is decreasing. What will be the induced, the direction of the induced current in the outer? Can you try this, please? Yes, there will be a comment section. Please try it and tell me whether it's clockwise or anti-clockwise. I'll be able to reply you on the comments. Please, if you like my videos, press the like button and please subscribe. I want us to really hit the subject that we want to make it difficult for the examiners to set the questions that we are unable to answer. Thank you so much. Thank you so much. Thank you so much. I think I'll end here. I hope you have enjoyed the video. Bye.